Chapter 3 looks at the atoms and elements that we're going to be working with as chemists. The first section was one that you should read in your book, and this kind of just gives a brief overview of that information. And then section 2, talking about the periodic table. First, we want to talk about Dmitri Mendeleev, and there's a TED video for you to watch, talk about his past and why he's so important for us in our discussion of the periodic table. Before we jump into the periodic table, just to give you a little bit more background, more just kind of something to think about as to why people like Mendeleev was so important during his time. When Jöns Jacob Berzelius was around, he developed the symbols that we use today. Basically kind of, well, before he was around in the 1750s, there was about 15 elements that were known. That's all they had to work with. Then around, basically during his lifetime, there's about 40 more elements discovered. So a lot of elements there. Now, and that kind of stems into why Berzelius was starting to look at some sort of organization, was because they had this massive intake of new elements. They had to have some way to organize them better than just having, maybe a stack of elements and things that they knew about them. So that was kind of why Mendeleev started looking at making this sort of table. And the awesome thing about once Mendeleev formed his table is that in the 1900s, kind of and beyond, so up to present day, there's been roughly 50 additional elements discovered. Many of those elements were prompted to go out and look for by Mendeleev's periodic table. So it truly is a very, very powerful piece of history for us. So let's fast forward now to present day and talk about our periodic table. By the way, for chapter 3, I use kind of this fill-in-the-blank type notes. This file is available on the Moodle site, so you can download it and print it if you'd like. This is our modern-day periodic table. It is basically morphed from Mendeleev's table to include all of our current day information and all of the elements. And currently, to date, there are 118 known elements. They are not all naturally occurring. And in fact, as we discover more and more elements, they are actually going to be man-made. So looking at the periodic table, depending on when your periodic table is published, this basically have this entire section here complete. Not all of them are named, but we do have that table complete. So this is basically just our periodic table. It gives us a lot of information. Okay? Some vocabulary for us to look at are, we organize the periodic table in groups. These are our columns. And our group labels are located above. So this is group 1A. Has hydrogen, lithium, sodium, potassium, rubidium here, cesium, francium. These are all in group 1A. We have group 2A here, beryllium, magnesium, calcium. Then the A groups continue over here with boron. We have in group 3A boron, aluminum, gallium, indium, and thallium. And 4A, 5A, 6A, 7A, and 8A. You'll notice I skipped over this middle section. These are the group B elements, and their numbering is not as logical as the ones for group A. And the numbering for us really doesn't mean anything. We're not going to use it. So we just refer to this whole section as group B. And that's that whole entire section there. That's group B. Our rows we call periods. And most periodic tables leave the numbering off, but basically we just number them going straight down, starting with hydrogen. All right. This lanthanide and actinide series, these actually, even though in most periodic tables they're pulled out and they're listed down below, they actually belong right here in the periodic table. Okay, so you just kind of split that apart, insert these two rows. Part of the reason why they're pulled out is they have a different set of characteristics than those in this main periodic table. Also, it's really so that it can fit conveniently on a 8.5 by 11 sheet of paper. Okay. So a lot of it is convenience sake. We aren't going to work too much with any of these elements down here until we get into chapter 4 at the very end of the quarter. Another piece of information on the periodic table that we're given is this bold line here, zigzagging its way down the periodic table. This is a very technical term here called the jagged line. And some people call it maybe the stair step. Basically what it does is it splits our periodic table in half. Okay, so when I refer to kind of left-hand side versus right-hand side, I'm talking about this jagged line. Even though, yes, we have plenty more elements over on the left-hand side, we kind of just consider this the split point of our periodic table, and we'll see more of that in a moment. So that's a basic introduction to our periodic table. We're going to learn a lot more about it as we go through chapter 3 and talk about kind of what are the different components, the different numbers, and so on and so forth. And we'll also learn a little bit as to why it's shaped this way. Most of you may think, hey, why can't we just put it in a nice, neat rectangle? We'll have all complete columns and rows, and we'll call it good. This shape is very particular, and it gives us a lot of information just solely by the shape of how it's presented. So it's very important for us. Some more classifications here. Our metals, these are going to be items that, or elements that are to the left of the jagged line. Okay. So remember I said we're splitting the periodic table in half. So all of our metals are to the left here. In this particular periodic table that I have on the print out, all of the yellow shaded elements are metals. Shading is not consistent from periodic table to periodic table, so be careful with looking at shading there. Our exception to that is hydrogen. Okay, hydrogen, actually we listed over here in group 1A, but sometimes we can consider it over here right next to helium. Okay, it is shaded blue, so it does belong kind of over here on occasion. Hydrogen likes to be the exception to just about every rule in chemistry. Our nonmetals, these are to the right of the jagged line. And I have except hydrogen here. Hydrogen can kind of swing both ways. Most of the time we consider hydrogen a nonmetal, okay, especially for this class. So that's in, maybe double parentheses. The metalloids are on the jagged line. Okay, and that one exception there is aluminum. Aluminum is a metal. And these are the elements that physically touch the jagged line. So they're represented by the green shading on this particular periodic table. So what's kind of the difference between these three classifications? Okay, that is important for us. Our metals, these are going to be elements that in their natural state, they're going to be shiny. They are what we call ductile. Okay, they can be pounded into thin sheets. They can be pulled into wires, you know, copper wires, things like that, electronics. And they're going to have a really high melting point. And we shorthand melting point MP. And basically what that means for us, our metals are generally going to be solid at room temperature. Here's another shorthand for you. RT is room temperature. The one exception of this, so except mercury. Mercury is actually a liquid at room temperature. In this particular periodic table, the phase that each of the elements are found in their natural state are represented by the coloring of the symbols. So all of the black elements are solids. Mercury here is a liquid. That's represented by the reddish color. Now our nonmetals, remember, are to the right of the periodic table. Okay. Most of those are gases, okay, represented by the blue shading here. Now, not all of them. We have carbon, phosphorus, sulfur, and selenium. These are solids, okay, and bromine here is a liquid. But kind of in general, we have that they are gases. So let's talk about our nonmetals. Okay. So kind of generally, gases at room temperature. Very generally, though. Our nonmetals are basically the opposite of our metals. Okay? Instead of being shiny, they are very dull. Instead of being ductile, they're very brittle. If we take, say, a hammer to them and pound them out, they're just going to shatter. And they're going to have very low melting points compared to your metals, which is why generally we're looking at gases. Our metalloids, these are the ones that are on the jagged line. Okay, so they're in between our metals and nonmetals. So that means they're going to have kind of similar properties to both. They're going to walk both sides of that line. So they're going to be shiny like metals, but they're going to be brittle like the nonmetals. However, we'll notice here the shading of the symbol or the font color is black, which means that they are solids at room temperature, which means they're going to have generally a high melting point. In general, not quite as high as the metals, but enough to be solids at room temperature. Some more vocab for us. Okay. Certain groups have very particular characteristics to them, such that they do the same type of reacting, so that we give them a special name because they react very specially. The alkali metals, these are all in group 1A. Okay, so lithium, sodium, potassium, rubidium, cesium, francium. These are the alkali metals. The alkaline earth metals, the next vocab word there, that's in group 2A. So we have beryllium, magnesium, calcium, strontium, barium, and radium. Those are all alkaline earth metals. The halogens are in group 7A, and our noble gases are in group 8A. So our halogens, we have fluorine, chlorine, bromine, and iodine. Those are our halogens. This astatine, the AT, this is not considered a halogen because it is a metalloid. Then our noble gases, we have helium, neon, argon, krypton, xenon, and radon. Then our last group are transition metals. These are all what's located in group B. So basically everything in this center block we call a transition metal. So that's our basic introduction to the periodic table. Work through your questions and problems and your sapling learning questions. And once you get that down, we'll move on into section 3, talking about the atom.